Oh, all right. Can you hear me? Excellent. Okay. Well, we'll try this one last time. If not, I guess I'll have to record it and then try again. Okay. So today we're talking about helical extension springs. Last time we talked about helical compression springs. We'll also be talking about torsion springs and spring washers. And this will conclude our spring lecture. I updated the syllabus. It's on Canvas. You can check it out. Helical extension springs are loaded. They're a lot like compression springs, but they're loaded in tension, and they have a certain preload force that has to be overcome before they start to move. So when you pull on them, you're not going to instantly get deflection until you overcome that initial pull force. The number of coils in the spring is NT, and that's the number of active coils plus 1. And then the body length is the diameter times the number of coils. Okay, so that's just this this length right here. So you can count your number of coils, add 1 to it to count for these guys here. That gives you your body length. The free length is the hook inside to the hook inside distance. Okay, so that's from here down to here, and that's the free length of the spring. The free length changes based upon the end configuration. So obviously if you have, like up here, you have this really long hook on the end, your free length would include from here all the way to here. The spring rate is the same thing as the force over the displacement, but in this case we have this extra term here, which is the initial force that has to be overcome before the spring starts to move. You can see that graphically over here, where we apply force, we apply force, we apply force. We don't get any deflection until we get to the initial preload force. And then once we get to that force and we exceed it, then we get our spring rate for a linear spring. And most of these are linear springs when we talk about helical extension springs. If we have a circular spring, this is the spring rate here. So if we have forces specified, we can calculate the spring rate from here, or we can calculate the spring rate from the geometry. But we have to keep in mind that that's only going to be active after the preload force. Okay. The spring index is the same as it was before. That's the mean diameter of the overall spring from here to here, divided by the coil diameter D. And the spring index, just like we saw last time, should be about 4 to 12 as a good starting place for design. Okay, the preload force can be somewhat controlled, so there's some design freedom over the preload. And then the initial coil stress we can find from the spring index. Okay, so we have a preferred minimum and a preferred maximum spring stress as a function of the spring index, and this is where we would like to operate. Okay, so the coil spring has an initial stress because the way that it's designed, it pulls the spring together up to the preload, and this is the sort of the design range that we would like to operate in. Okay, and it's based on the coil index. Okay, so you can use these expressions in software to calculate your initial stresses based upon a design. The spring deflection has almost the same equation as before, except we subtract that preload value to get the deflection of the spring. That's the diameter, the mean diameter cubed times the number of active coils over the coil diameter over the shear modulus of the spring. The stress is the same as before, and it's a shear stress here that's applied because of the force. And if we have a static case, we can use this factor here as Ks. That's a function of the spring rate. I'm sorry, that's a function of the spring index, C. If we have a dynamic case, we have to consider stress concentrations like we saw last time. We'll use this KW, and the KW actually includes this KS plus a KC, which is the curvature, which we talked about last time. So these are the same expressions that we had last time. When we have a spring, we'll have a stress. Okay, usually we're applying the load here in this direction, and that causes a bending moment here on a curved beam here. And these are the equations that calculate the stress at A. Okay, so we can find these parameters. KB is a function of this C1 here, which is twice the R1 over D. Okay, and R1 is this bend, the internal bend radius. We also have a shear, torsional shear stress due to that loading here. Okay, so if you look here, the load is offset. Okay, when it pulls on the end of the spring, we have a bend radius here, which causes a little bit of a stress concentration, so we have to include that. And we have the max torsional stress at this location here on the outside of this beam because we have a load here and it wants to cause this guy to twist. Okay, so it causes a torsional shear stress right there, and the torsional shear stress here has been found by experimentation. These parameters here, which are a function of C2, in this case C2 is twice R2 over D, and the R2 is this inner bend radius of that spring. Okay, C2 should be greater than 4 for design constraints. And obviously, when you go and buy off-the-shelf springs, most of these design considerations and requirements are already taken into consideration. Okay. So the natural frequency of the spring is the same, and we have to remember to stay, 13 times 13x away, if possible, from the natural frequency to avoid surging of the spring. Okay, so that's just the same equation that we had in the helical springs. And the wires are also the same as the helical compression springs, but in this case they're loaded in tension. When they're loaded in tension, it causes torsion on the springs, and so we use the torsional strengths, and the torsional strengths are the same. So these are our endurance limits for steel unpeeled wires. This is the uncorrected endurance limit. If you have unpeened springs, this is the endurance limit. If you have peened springs, this is what we saw before. So we can calculate the fully reversed stress point here. This is SES, which is point C. Okay, as a function of our corrected endurance limits, our ultimate strength and shear, and over this denominator. We can plug this into here with our ultimate shear, and then our initial, our inner diameter shear stress, our mean shear stress, inner diameter stress, and the alternating stress to calculate the safety factor like we did before. Excuse me. Okay, so we have to consider the static and dynamic case. This is the maximum torsional and bending yield strengths for helical extension springs and static applications. Okay, this table here is the maximum torsional and bending fatigue strengths uncorrected for these two different types of wire, the A228 and the 302 stainless, with a stress ratio of 0. Okay, and this is the percentage of the ultimate tensile strength. So we'd get our SUT from the material properties, and we would multiply, depending on the fatigue life, the corresponding parameters. Okay, the body of the spring, and this is the end of the spring. The body of the spring, the end of the spring. The body of the spring, end of the spring. So you can see that the fatigue life, if the spring is going to fail in fatigue, it's most likely going to fail at the end. Okay. All right, so the design process is essentially the same for helical extension, helical compression springs, but we have to consider the details at the ends as well. Okay. The process is as before, where we have to start with a geometry and then iterate through the design to meet the static and fatigue requirements, which are usually expressed in terms of safety factors. And the design process is to pick a spring index. We usually want to pick between 4 and 12. Calculate the coil stresses from those equations. These are our initial stresses. Calculate the preload. And then once we have the preload, we can find our initial stresses, make sure that they're fine. And then we can calculate, based on an assumed load or a stated load, we can calculate the coil and end stresses. Okay, so these are the coil stresses that we just saw from the previous slide, where this F is the applied load then, instead of the initial load. And then we have the end stress, and then the end stresses here are due to the bending stress from the stress that's applied to the rod, the beam, the spring diameter, and then we can calculate the shear stresses as well. Okay. And then we can calculate the deflection and natural frequency to avoid spring surge and make sure that we meet our dynamic and static safety factors. Okay, and we have to consider the torsion in the coil, the bending and shear at the ends. So this is the design process. This is the design of a helical extension spring for cyclical loading. It says, this is an example, a spring must have a minimum force of 50 pounds and a maximum force of 85 pounds over a dynamic deflection of ½ inch. The forcing frequency is 500 RPMs. Infinite life is desired. Standard hooks will be used at each end. Music wire, which is the most commonly used spring material, as ASTM A228, will be used, since it's also good in fatigue. Setting and peening cannot be used to obtain higher endurance strength, so we'll ignore that in an extension spring. And so we start with a trial diameter. So in this case, we pick a 0.177 trial diameter from the available sizes from the table that we saw in the last lecture. We pick a spring index between 4 and 12. In his case, we picked 9, and we use it to calculate the mean coil diameter from the spring index. So spring index is the mean diameter over the coil diameter. So we just do 9 times the coil diameter to get the mean coil diameter of that spring. So once we have that mean coil diameter, we have the spring index, we can find the appropriate initial values of the coil stresses. So we just plug in C into those shear stress equations, and this is the minimum and maximum stresses that we should have. And so, okay, and so here this is 9,744, 16,699 psi. So we'll say, well, the initial stress is going to be, let's pick it to be between the two. So we take the average and find it to be 13,237 psi. So then we want to find the direct shear. Okay, and so if we find the shear factor from the equation that includes the spring index, we find it to be 1.06. And then we use the KS and the value for the shear. Okay, and then we plug it in here and solve for the initial force. Okay, so that's the initial force that we have to apply to get the spring to begin to move. Okay, so then we have to check and make sure that this force is less than the required minimum force, which in this case it is, okay, because we have the minimum force here is 50 pounds. So what we can do then is, based upon the 50 to 85 pound range, we can get our alternating forces and our mean forces, which is we have the difference of the max and min over 2, and then we have the sum of the max and min over 2. Okay, so we have an alternating force of 17.5 pounds, and we have a mean force of 67 pounds. Okay, so then we'll use the direct shear number, and then we'll calculate the mean shear stress from the mean force that we just saw up here. And we find that's 52,122 psi. Since this is a forcing frequency, it's dynamic, so we're going to have to include the wall factor because we have a dynamic stress concentration. We can calculate the wall factor, and then we apply the wall factor to the alternating force to get our alternating shear stress. And we get that to be 14,877 psi. Okay. So then we can find the ultimate stress either from the equation or the table. We use the equation here for that wire with that diameter, and we can get the coefficient A and exponent B from the table to calculate our ultimate tensile strength. Then we can get our ultimate shear strength, which is 67% of the ultimate tensile strength. And then we can get our yield strength, which is 45% of the ultimate tensile strength. Okay. So then we have what we need to begin to calculate our endurance limits and safety factors. Okay. So we find the endurance limit for the unpeened springs. That's from the table. It says that it's a percentage of it, and then we can convert it to a fully reversed endurance strength with that equation. That's just finding the point that's finding the point of the intersection for the low cycle fatigue at 10 to the 3 that we saw before. So once we have that, we can calculate that. We can plug in our values and get our endurance limit here of 2680 psi. Okay. Then we can find the safety factor for the coils and torsion, which we just had in the previous slide. And in this case, we use the minimum stress due to the minimum force, not the coil winding stress. Okay. Okay. So then we can calculate the alternating mean and mean stresses from the minimum stress, the mean stress, and the alternating stress. So we get our different values there. And then we convert the torsional endurance strength to the tensile endurance strength and use the ultimate tensile strength to find the safety factor. Okay. And so we can plug those values in for the minimum, mean, min, and alternating stresses. This is from the Goodman diagram here. This SE, that's the 67% of the endurance limit there. And then we find that the safety factor is 0.78, which is too low. Okay. The torsional stress in the hook are found from the equations for the shear stress. Okay. So we can calculate those. And then we can look at the hook's safety factor by plugging the values in for the alternating minimum and maximum bending stress, shear stress, the torsional stress, and we get a safety factor of 1.1. Okay, because this safety factor is less than 1, okay, this is not an acceptable design. And then in order to prove it, there's a list of values of the spring index from 4 to 14. Okay, so this is the spring index, and this is the effect of the spring index on different spring parameters, either the length, the weight, or the fatigue ratio. Okay, so this is the total weight of the spring as a function of the spring index. This is the free length as a function of the spring index. And this is for a constant wire diameter. This is the outside diameter. Okay, and this is the safety factor for the coils and torsion. This is the safety factor for the hook and bending. Okay, so we have to be somewhere above 1 in the safety factor. okay? And so we need to be over here because we started with a spring index of 9. You can see that a spring index of 9, that gives us that safety factor that's less than 1. So we'd have to drop the spring index in order to correct the design, okay? So if we go from 9 to 7.5, then we are in the range here where our safety factors for the hook and bending, the hook of the spring and bending, and the safety factor of the coils and torsion are both going to be greater than 1. Okay, so if we recalculate everything with a spring index of 7.5, we get these values for the stresses. We can plug those into the Goodman diagram to find the distance to the failure line. And we can find the safety factors here are all greater than 1. So then we can complete the design. The spring rate is defined as 85 minus 50. That's the working range. That's the initial load that we're going to see on it. And the rate has to be 70 pounds per inch. Okay. So if we want to get that spring rate, then we have to pick the number of coils in order to get that K. So we can plug K in or solve for the number of active coils based upon the spring parameters that we found that will correct our stresses. So as you can see here, we didn't define how long the spring was. We first picked a spring index and a spring diameter, and then we calculated the stresses based upon the working loads. Okay, and then calculated the safety factors based upon the minimum, maximum, and alternating loads. And only then did we go and try to define the rest of the spring. Okay. All right. And so now that we have it, you can go to the nearest quarter coil, and that gives you a spring rate of 70.7, which defines the rest of the parameters. Here we have the number of coils, okay, which is active coils plus 1, and then we have our the length of the body of the spring, and then we have the free length. Okay, and the free length is going to be the length of the body plus twice the length of the hook. Okay. The length of a standard hook is equal to the coil inside diameter, so we just add twice the inside diameter to the body length to get the overall length of the spring. Okay. Now that we have the number of active coils, we can actually find the natural frequency. And we calculate the natural frequency, and we find that it's 140.6 hertz. Okay, so it's 146 per second. So if we multiply this by 2 pi, or 1 revolution per 2 pi, and then multiply it by 60 seconds in a minute, then we have 8,436 revolutions per minute. The ratio between the natural frequency and the forcing frequency, which is 500, is 16.9, which is perfect because we said we want it to be about above 13. So then we satisfy that design. Okay. So then we have our final design, our spring diameter, our coil diameter, outer diameter of the spring, the number of coils, and the free length. And then we can find a spring that meets that. This is just a table of the design parameters, okay, and how they are used, okay. So you can see the benefit of, if you set all this up in software, then you can, such as EES, then you can use that, okay. So are there any questions? Okay, So we've talked about helical extension springs, that we've talked about helical compression springs, and we're going to talk about helical torsion springs. Okay, so helical compression springs provide a push. Helical torsion springs provide a torque. Helical extension springs provide a pull, and then helical torsional springs provide a twist or a torque or a moment. Okay, the helical torsion springs are loaded in torsion, which causes bending stress. Okay, so when you apply bending here, these are like curved beams, and you're causing bending stresses. The ends are extended tangentially to provide these lever arms so that you can assemble them in the housing. And usually this end will move relative to this end, and you always want to apply the load so as to close the spring or bring this end in a clockwise fashion towards this end, okay? Or bring this end in a clockwise fashion towards this end if you're looking at this side. The coils are usually closely round. There is some friction that you'll have there. There's usually no preload tension. The applied moment, as we said earlier, when you apply a moment, you're bending these beams. When you're pushing on these lever arms, causes bending in these curved beams. The applied moment should always try to close the spring. Okay, you don't ever want to use these where you're using them to open the spring. Okay, so you'll that's a design rule of thumb. Because of the way that they're made, there's residual stresses that are in your favor if you try to close the spring, but they are not in your favor if you try to open the spring. Okay, so the dynamic loading should be repeated or fluctuating. That means we don't want reversed loading. Okay, so we don't want to have loading conditions where we're trying to open the springs. At least 3 radial coil supports are required for the reaction forces. Okay, so you'd usually have one on the end, one in the middle, one on the other end. Or what's typically done is there's an internal rod that's placed inside of the helical torsional spring, and you choose the rod such that it's less than 90% of the inner diameter. And the reason you do that is because when you apply a load to a torsional spring, it starts to close the spring and make the spring inner diameter get smaller. So you want about a 10% gap between the two so that you can close the spring. Okay, so these are the helical torsional spring defining parameters. Okay, here we see the rod here with the room for it to close. Okay, this is alpha. Okay, that's the angle between the ends. F is the load on the ends. L is the moment arm for that load. Theta is the angular deflection from the free position. Okay, so these are our parameters. We have the same parameters that we had before for the mean diameters, coil diameter, inner and outer diameters, but we have a new term here, which is the number of effective coils. And the number of effective coils includes the length of the ends here, these L's, L1 here and L2. Okay, and those are the effective lengths of the ends. Okay, and then you have a number of effective coils, L1 plus L2 over 3 pi d. So that gives you like whatever the effective coils of these lengths would actually be for your overall spring. And from that, we can calculate the number of active coils as the number of coils in the body plus the number of effective coils that you get from these free ends. Spring rate is the same, but instead of it being in terms of force per unit deflection, we use it in terms of moment per unit angular deflection. LW is the length of the wire. Okay, and the length of the wire comes into your deflection equation. Okay, so your theta in terms of revolutions, which is sometimes it's easier for people to understand than radians, can be converted from calculating your angle in radians and multiplying it 1 over 2 pi. And then you can get your deflection in radians as the applied moment times the length of the wire over your Young's modulus times your moment of inertia for the wire. If we have round wire, we can plug those values in and we can find that theta in terms of revolutions, that's this theta, is 10.2 times the applied moment times the mean diameter times the number of active coils times divided by the coil diameter to the 4th power times Young's modulus. Because there is friction in the coils as they rub together, they actually have an effect, and the effect is accounted for by saying that the theta revolution is approximately 10.8 times these parameters. Okay, so these are the defining parameters for the torsional spring. Okay, the spring rate is the moment over the deflection, which we said. Okay, and we can find that with these parameters here. The coil closure diameter and length, we said that when we apply a load, or when the loads are such that it causes the spring to close, we'll actually get a closure diameter, and that's the diameter that we get that's based upon the deflection. Okay, so the diameter will get smaller as we get larger and larger deflection. Okay, and that's shown here with this expression here. L max is the max length of the spring, and that includes the angular deflection here. Now, because of the way the spring is loaded, we actually have bending stresses. We know that our bending stress comes from our flexural formula. Okay, and Wall did a number of experiments, as he's done for the other types of springs for curved beams, and found the parameters in terms of the spring index for us for the inner and outer stresses on the coil diameter. Okay, so we have an expression for the inner diameter. This is the max inner diameter force, which uses this KBI. It's the inner diameter, which takes our max moment times our distance to the neutral axis over I. And if we plug in the parameters for a wire, we get this expression here. Okay, and that's the inside diameter. And these are compressive stresses. Okay, so these are a bigger concern. This is the biggest concern for static failure. Okay, because it will these will be the largest compressive stresses. We also can calculate the stresses on the outer diameter, the min and the mean stresses. The min and max stresses on the outer diameter are given by these expressions here. And these are the outside diameter tensile stresses, and they're the biggest concern for fatigue failure, because we know that tensile stress reduces the fatigue life and compressive stress increases the fatigue life. And so if we have a fatigue application or we have cyclical loading, then we are more concerned with these stresses here that will be of concern for fatigue failure. Okay, and that's the outer diameter stresses. Okay. If the coil spring is loaded to open its coils, which is not recommended, then it must be stress relieved or shot peened. Okay, to remove the residual tensile stresses at the outside diameter. All right. So for helical torsional springs, these are the max bending yield or max bending fatigue failure stresses. Okay, and these are expressed as the percentage of the ultimate tensile strength for that material. Okay, so these are give you a couple different materials. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these encompass most of the springs that we have in the original table for the different springs. And this is the maximum percentage of the ultimate tensile strength. So if they're not stress relieved through shot peening or annealing, I'm sorry, if they're just stress relieved, okay, but they don't have favorable residual stress, then we use a lower percentage of the ultimate tensile strength. Okay, this is for the bending yield. This is for static applications. If we have bending fatigue here, okay, then we can look at the percentage of ultimate strength, and this is the fatigue strength for 10 to the 5 and 10 to the 6 cycles for both unpeened and peened materials. Okay, for music, I think it's music wire, and stainless, or these other parameters here. So we just multiply that percentage of it. Okay. Okay, so for bending fatigue, we have this factor here, which is for bending. Okay, as this is the endurance limit that we get from this table, and if we convert it to bending, it's 0.577. Okay, so if we plug these numbers in for the endurance limits of the wires, then we can get our endurance limits for the bending fatigue to be 78 kpsi, for example, for unpeened springs, and 117 kpsi for peened springs. The safety factor for failure and yielding would just be the yield stress over the inner diameter max bending stress. And for fatigue, it's the fatigue and bending for that spring, and that's the endurance limit times the ultimate tensile strength minus the outer diameter minimum stress over the endurance limit times the difference between the outer diameter mean stress and minimum stress plus the ultimate tensile strength times the outer diameter alternating load. Okay, so you'd have to calculate these loads for each of those locations on the spring. We can find the point for fully reversed stress. That's the y-axis intersection of the Goodman diagram from this equation, where we're just solving for that value for the fully reversed stress in terms of the ultimate tensile strength and the endurance limit. Okay, so this is how we use it. This is an example which is in your book. It shows us how we can walk through that. It has us design a torsional spring for a dynamic load over a given deflection. There we're told that we have to have a minimum moment of 50 inch-pounds and a maximum moment of 80 inch-pounds over a deflection of 0.25 revolutions, which is 90 degrees, and we want an infinite life. We're going to use unpeened music wire again and use 2-inch long straight tangent ends. Okay, that gives us the effective length, the effective coils for the ends. We can calculate those. It says the coil is loaded to close it, which is what we want. And so what we do is we pick a trial diameter and a spring index, okay? And then we can calculate the mean and alternating moments as the sum over 2 and the difference over 2. And then we can calculate our wall factor. Then once we have the wall factor, we can calculate the inner bending moment stress from that modified flexural formula from wall and find the stress there. And then we can do the same thing for the outside surfaces and calculate the minimum alternating mean and tensile stresses in the coil. Okay, so we find our bending stress on the outside. We get the minimum from the stated moment. In this case, it's 50. The maximum from the stated moment, which is 80. And that comes from the 50 and 80 that we have up here. And we calculate those min and max moments. Once we have those, we can get our mean and alternating stresses, okay, from our applied mean and alternating moments. just like we did for the fatigue analysis. Okay. Then we want to find the ultimate tensile strength for that wire. So we can go to the table, find the A coefficient and the B exponent, and find our ultimate tensile strength. And then we can use it to find the bending yield strength for the coil. And in this case, we assume no stress relieving, so we have 100% of the ultimate tensile strength. Okay, that comes from this table over here. Okay, where we have no stress relieving. We have favorable residual stress, so we have this parameter is 1 for the yield stress. That's the static case. And then we can find the wire bending stress endurance limit for unpinned springs, and then convert it to fully reversed endurance strength, which is just finding that point on the Goodman diagram. Okay, so we do that. We take the 45,000 over 0.577. Okay, and that gives us 77,990. Then we can find that fully reversed point on the Goodman diagram, which is SE, and then we can put those values in to find the safety factor. Okay, so we find the safety factor for the coils in bending is 1.4. We find the static safety factor, which uses this stress, which is related to the yield stress over the applied inner diameter maximum stress. We find the safety factor is 2. So these are both acceptable safety factors. The spring rate we can define then is the change in moment over the deflection. Okay, so that's 120 pounds per inch per revolution. And then in order for us to get that defined spring rate, we have to pick the number of coils. Okay, so we solve for the number of active coils, and we get 18.2. We know that the ends contribute to the active coils, so we have to add twice 0.25 to get the body length of the spring. Okay, so that gets us about 18 for a body length of the spring, and then we can calculate the min and max deflections, and the min deflection is 150 degrees, the max deflection is 240 degrees. Okay, this was from that previous example, which just showed the parameter changes as a function of the spring index for a constant coil length. Okay, so the last topic that we're going to talk about is Belleville Washers. These are also called disc springs or cup springs, and they are nonlinear springs in general. And they're little cone-shaped springs or discs. They have a thickness T. They have an inner diameter Di, outer diameter Do, and then they have this diameter ratio here, RD, which is the outer diameter over the inner diameter. Okay, the RD parameter affects the energy storage capacity of the spring, and the height, which is the height that is off the ground from here to the bottom. Okay, this height of the spring defines the spring rate. Okay, these springs are used in so many different applications, and they're compact. They're capable of large push forces over small deflections per washer. And they should be operated between 15 to 85% of H. So you can see these are not very tall. Okay, so 15 to 85% is a small range. Okay, but they show up in a lot of applications. What's interesting about them is that you can get different behavior based upon your height to thickness ratios. If you have a height to thickness ratio of 0.4, then you get almost linear behavior. Okay, and this is the percentage deflection to flat. Okay, so if you go up here, that's 100%. That's 100% flat. So if the spring is laid up against a flat surface, you can only go from here to here. If the spring, on the other hand, is in an orientation like this, where it can actually travel through the neutral deflection or the flat deflection all the way to the other side, where it can come all the way down here, then you can get this second half of this graph. Okay, Now, what's interesting is that if you pick different height to thickness ratios, you can actually get a spring that is bimodal, or a spring that has a nearly constant region. For example, if you pick the height to thickness ratio of 1.41, then as you go from 0 to about 80% deflection, you have this nonlinear parabolic looking profile. But then if you go from 80% to 120% deflection, you have almost a constant force spring. Okay, so you can use this in your design if you need small deflections and at 100% of the force to flat, you want a constant force. You can design that with these cool little Belleville Springs. Okay, the force is a function. Okay, one thing I want to note though, if you get a higher than 1.41 region, you get these regions here where you have a spring that is bistable. Okay, so it's bimodal and bistable. Okay, if it's allowed to traverse beyond the flat. Okay, so for the same for the same load, you have two deflections that you could actually be at. Okay. The force is a function of the height and the thickness of that spring, and this parameter K1. And the parameter K1 is a function of this diameter ratio. If you plug in Y equal to H for the flat, you can calculate the force required for your spring to go fully flat using this equation. In this equation, the mu here is Poisson's ratio. The stresses in the springs that we care about are at the ends here, the ends of the springs. So if we took a cross section of the springs, we care about the stresses here, here, and here. In fact, this sigma C at the top surface is the maximum stress. These are the equations to calculate the stresses at those different points. Okay, so we have the TO, sigma TI, and sigma C. And these are sigma Ti and sigma TO are both in tension, and sigma C is in compression, and it is the greatest of the three stresses. So here you can just plug and chug based upon your spring parameters, and you can calculate your spring from its height and calculate the force, the stress that you experience at a certain deflection. Since the compressive stress is the largest of the stresses, it actually causes local yielding and strain hardening, and because of that, we can have stresses that are actually higher than the ultimate tensile strength. Okay, and recall that when we have even materials, the ultimate tensile strength is equal to the ultimate compressive strength. And if the spring is dynamically loaded, then the inner and outer stresses should be calculated as well, and the mean and alternating stress is identified and used to design the Goodman diagram. Okay, so these are the maximum recommended compressive stresses for sigma C for Belleville washers in static applications if we have an even material where the ultimate compressive stress is equal to the ultimate tensile strength. Okay. So if the spring is set removed, then we can have much higher percentages. Okay, if it's carbon or alloy steel, we can have 120% of the maximum percent ultimate tensile strength. So in this case, we can actually have higher stresses at that location in the spring and still not fail. Bevel springs can actually, since they have a relatively small deflection, which is not always desirable, they can be stacked to increase their overall deflection, and actually you can put them in parallel, in series, or in series parallel, and get different behavior. In this case, if we have a parallel stack, the forces add because the forces from all of them are seeking to resist this motion. And the deflections, it's the same as the deflection for one spring. Okay, so if you needed twice the force over the same deflection, you can just drop in to Belleville Springs. In a series stack, the forces are the same as one spring, but the deflections add. Okay, so then we can get, for the same force, if we add more springs, we can get twice the deflection for 2 springs, all the way up to however many springs we have. If we have a series parallel stack, the forces are the same as in springs, and the deflections add according to how many you have in series. Okay, so it's a pretty cool it's a pretty versatile spring. Okay, so how do we design them? Well, we design the same way that we design other things, and that is we have to start somewhere and then see if our design works or if it's bad or whatever. Okay, so the place to start for Belleville Springs is to start with a height over thickness ratio and pick a outer and inner diameter. If you know the force or displacement curve, that should kind of inform your height over thickness. For example, if you want linear displacement, then your H over T ratio should be the 1.41. If the force range or value is specified, okay, then the deflection can be calculated using these equations, which you can plug these equations in and solve for Y and EES and play around with different parameters. Or given F, you can estimate the thickness from this equation. Now, this might be a little bit confusing to you because we have T over here and we have T over here, but keep in mind this is the H over T ratio, okay, that we're picking based on the deflection. So we're not necessarily defining T, we're just plugging in that ratio so we can solve for this T here. Okay, so this is the example of designing a Belleville spring to give you constant load over a given deflection. Okay, we're not going to walk through this now because this is in your notes and you can calculate them based upon the parameters that we just went over. And we'll go ahead and stop the lecture here. And if you have any questions, please let me know.